We saw in the previous foiling tutorial how to create a new foil for any board. We are now going to go a little further in the design of the foil and see the tools for adjusting the foil according to its hydrodynamics. For this project, we are going to use a board specially dedicated to foiling. A prototype of the Foon brand, with an original shape. In fact, you can put a foil on any board. In theory. Then, will it work? This is a question that hydrodynamic analysis can solve. But in the dynamic software, we can select any board from our database, here in our library, and decide to put a foil on it. Here, we have chosen a board, which is a bit special, with a volume that is intended for foiling. We have already put a foil on it. We will now see how to analyze the performance of the foil, and how to adapt the wingspan and the position of the foil, depending on the project. So in the Fin Management tab, here at the foil level, we select the tool, Foil Hydrodynamics tool. So there, we go into hydrodynamics, we will have to switch to the dynamic option. So we have a proposal to switch to the board dynamics option. We click on yes. As a reminder, the board dynamics option allows us to have access to test tools here on the right, which will allow us to test the position of the surfer at a given speed on the foil. On the right, here in my interface, if I select a surfer position, I will know the performance of foiling at this position. What we see in this interface is that, at the given speed, at 5 meters seconds, we are in the possibility of foiling. The surfer who is selected in the project is an 80 kilo surfer, his weight is given here. The slope is 0 degrees. This corresponds to a towed surf configuration. We can position the surfer. The information here at the top gives us the speed, 5 meters seconds, and confirms that foiling is possible in this configuration there with an angle of attack of the board at -3 degrees. We are talking here about the angle of the reference plane of the board in relation to the level of the surface of the water. I can show the surface of the water. Here, we have the surface of the water, and we see that we have a negative angle. It is according to the settings of the foil that we obtain this result there. Even if there is a negative impact on the alignment of the board, in relation to the body of water, the foil has angles, which make it possible to generate lift. This foil is special, it has very arched profile shapes. And this is what makes it possible to generate lift, despite the negative angle of the board. We are going to show the vectors of the foil, in particular the resultant of the forces. So here we see the lift vector, which indicates its vertical component of 815 newtons, which corresponds to the weight of the surfer and his board. We will also see the pitch moment. The pitch moment indicates the state of balance, depending on the position of the surfer. Moment tells us the rotational force around an axis. Here, the moment that interests us is the tilting around the pitch axis. In the vector display options, I'm going to display the pitch moment. If I select the circle that represents the pitch moment, an indication gives me this moment. We have a moment of pitch here, which is 17 Newton meters, so this moment is positive. To visualize the positive or negative direction, we can grab the ring here and spin it. I tilt down, and I see that the pitch torque is positive. If I tilt up, we see that the moment becomes negative. My pitch torque being positive, so I will swing forward. I have a positive pitch moment, so I swing forward. I'm going to change the appearance of my board, in point view. And we see the three axes yaw, pitch, roll, of my board. These three axes intersect at the place where we positioned the surfer. In my diagram on the right, I'm going to advance my surfer here. And we see that the axes are moving. We see that the torque pitch has increased. It has increased to 260 newtons of forward tilt, which makes sense. We swing forward. By selecting my position on the right, I will go back step by step. And you can see in the diagram the pitch that is displayed. So I'm at 177 Newton meters, so I switch with a moment of 177 Newton meters, and if I step back, I see that this moment of pitch drops to reach a value almost zero. Here we can display 0.6 Newton meters. We can say that we are balanced, so I determined the position that the surfer must have in order to be in stable balance. We can also adjust this balance, visually, simply by observing the overall lift resultant. When the overall lift resultant of the foil crosses the surfer's support position, the moment is zero, and the balanced surfer. Here, I'm going to backtrack until the resulting vector intersects the center of the axis. I thus balanced the moment of pitch. So that's it for the graphic reading of the foil force alignment. We will see now the foil adjustment tool, which is here. I go to the Ends tab and I will open the foil tool. The foil adjustment interface has four main views. With a wheel, we can zoom and we can move the drawing. This allows you to take screenshots or take a closer look at certain things. Here we have the bottom view, and we see the different elements of our foil. We could modify the position of our foil using these tools on the right. For example, foil POSX. We can put an increment of 100 millimeters, and I will advance a little. So I advanced all of my foil, here on the right, or on the left. I can select a single part, and move only the main wing, or the stabilizer, here forwards or backwards. I can also change the wingspan of the foil. I will put a stronger increment, so that it is clearly visible, and there, I increase the wingspan by 100 millimeters. I selected global. So it's my two wings that will be enlarged. When we modify these elements, an update of the performance of the foil is carried out. For example, if I increase my wingspan here by 100 millimeters, I see that my drag for this wing increases. It has gone from 104. It was just now at 90. Here, we also have the recovery of the foil's drag information. Here we are only talking about the foil, and not the board. And we see that, with this wingspan, in this configuration, the foil has a total drag of 196 newtons. So we see the performance evolve according to the settings. We have modified the wingspan, the position. The position does not modify the drag. The position only modifies the moment of pitch. So in this top view diagram we see the surfer position appear. We see the two large-scale foil schemes appear. We have information on the width of the foil. Here on part 1 being the stabilizer, we also see its surface in square centimeters. And its distance from the tail, here, the leading edge of the stabilizer, is therefore at 208 millimeters from the tail. Same for the 0 part, which is the main wing, with a wingspan, area and distance from the tail. Here we have the total drag force. Here we have 196 newtons of drag. There is an interesting information for the designers of eFoil, for example. It is the power in watts of the propulsion necessary to fight these 196 newton of drag at 18 kilometers per hour. We now display the side view. The side view shows the reference plane of the board. The reference plane of a board comes tangent the lowest part at the wide point. So here we have the central rocker of the board, in red. And in green, the rail rocker. We have the plank reference plane here in black dotted lines. In this case, we have a flow attack of 3.3 degrees. The fluid moves along the gray line, which makes an angle of minus 3.3 degrees with the reference plane. A plank attack that is negative means the plank is pointing down. In this side view diagram, we see the pitch moment. This point represents the support position of the surfer. Here we are going to move this support position of the surfer a little forward. We move the position of the surfer. If we go forward, we approach the surfer more and more closer to the lift component of the wing. And we will thus come to reduce the pitch moment. We could thus reduce the pitch moment until finding the position of the surfer, where the moment is 0. We have of course an automatic function, which allows to align the surfer on the null moment. Here, the software aligns the position of the surfer at a null moment pitch. So balance the position of the surfer with the forces of the foil. We could do the opposite, and for example place the surfer at 0.2, here, and position the foil according to the position of the surfer. I no longer want to balance the surfer following the foil, but the foil following the surfer. This tool there moves the foil as a whole until you get a moment of 0 pitch. These balancing tools, balancing pitch moment, allow you to anticipate the positions of the surfer and the foil. Everything we have seen here has been calculated for a given speed and a given surfer weight. These are the equilibrium conditions visible here, which are 814 newtons of heavy force, which correspond to the 83 kilos of the surfer plus the weight of his board. And this was tested at the speed of 5 meters per second. But if I was at a lower speed, I would get into a situation where I didn't have enough lift. I show the other information with back view. Here, on the right, I have information which is important. It is the balance of the forces. With this surfer there, and in these speed conditions, we don't have enough lift to balance the surfer's weight. We have 147 newtons of lift for 814 newtons needed. So we could say that at 7.6 kilometers per hour here, my foil will not fly. We will be able to determine the correct wingspan of the foil, depending on the weight of the surfer and the desired speed. By knowing the wave speeds, we have a tool giving the crest speeds, depending on the wave height. We can say that for a wave of 1 meter, the crest and displacement speed of the waves is about 12 kilometers per hour, with a maximum surf speed of 20 kilometers per hour in a wave within a meter. So here, we come to find out about an order of magnitude of speed for our project. I want to make a foil that flies in a wave between 1 meter and 1 meter 50. So game that starts to take off at 12 kilometers per hour. So I come back to my foils tool with my information. I know I have to fly at 12 kilometers per hour. Here, I'm going to put myself at 12, 11, 9. And I see that I don't have enough lift. I have several solutions to increase the lift of my foil, which are, increase its wingspan, or increase its angle of attack. The problem with increasing the angle of attack is the degradation of the lift-drag ratio, i.e. the flight quality of my wing. So we will rather select as a first approach an increase in scale with a balanced weight force tool. The software will adapt the surface of the foil so that it flies at the pre-selected speed. Here, we are at 11.9 kilometers per hour. With this foil surface, we arrive to obtain the desired lift. What you should know about this function is that the software applies and uses the foil angle that produces the best efficiency, i.e. the best lift-drag ratio, i.e. the angle that will fly the best with the minimum drag, and therefore the minimum energy consumption. The quality of the foil varies according to the angle of attack. So we will select the angle of optimum incidence of the foil, so that it produces the best quality of flight. The quality of flight, given by the lift-drag ratio, here it is 18. To obtain propulsion generated by the slope, equal to the drag, we would need a slope of 3.2 degrees. So this foil is able to maintain its speed and flight, theoretically at 3.2 degrees of slope. Satisfied for these conditions, and this surfer, I can get out of the tool. And so there, now, I have a foil that corresponds to my desire to fly at 11.9 kilometers per hour. We update the position of the surfer. Voila, the hydrodynamic data of the foil are ready. I can now go and test my foil in my wave. I'm going to remove the display of the pitch moment, and I'm going to load my foil into the wave to do a little takeoff test in my wave with my foil. Here, it's a wave of 1 meter 20. Depending on the state of the computer, we can arrive at losses of the graphic display. This can be seen when we has at the bottom here on the left render off and that the 3D display is lost. To fix this, we just have to click on 3D reset at the top to restart the display. It can happen depending on the different software that are in use. So we recover the graphic display with 3D reset in the top left. So here I am in the wave room. I guess you have seen tutorials on wave design. Here we are in the wave, but we have not activated the board dynamics option. So we do not have our board in simulation. We will go to slow speed. So I'm going to activate the board dynamics option to make our board appear. So here we see the board. I'm going to display it in volume, and the foil is underneath. I'm going to slow down, I'm going to stop altogether. So we have a certain slope, and a certain surfer weight. So we see here that the weight of the surfer is not aligned with the resultant of the foil. This generates a pitch moment of 111 newtons meter. So the position of the surfer should be a little further back here, for this foil. Here the surfer is better aligned. Whereas, and I'm talking about surfer position, we're talking about the position of the center of support. The feet are generally around this center of support. It all depends on the position in which the surfer is standing. What matters for hydrodynamics is the position of the center of support. The position of the feet matters little to us. If we are squatting a little more forward or backward, we will vary this position of center of support. We can vary the center of support without changing the position of the feet. Just by tilting the torso forwards or backwards, this loads more or less the front or rear foot. The important thing, what counts, is our center of gravity in relation to the board. Here I display the pitch moment. And we see that the pitch torque is slightly negative. So I go back a bit. This is informative. In this simulation, we are not going to tilt the board forwards or backwards. Depending on the pitch, it's going to be neutral. We will have the information on the changeover, but we will not generate a real changeover. It would be totally unmanageable in terms of board control, because the slightest movement of the mouse would cause the board to tip over. So, we hypothesize that we are in a situation of equilibrium. So here, we just have information about the imbalance, but the software won't tilt the board. So the information is that we would have to be roughly here to be in balance. The other important piece of information will be the trajectory. We will display it here. We can modify the angle of the foil here. And at the same time, vary the trajectory. Here, we are stopped. We must restart the wave. So I'm not going to repeat the tutorials on time control in waves. Just for information, when we are in dynamic simulation, we have a slow speed, a fast speed, and a stop. The slow speed corresponds to real speed divided by 100. The fast speed corresponds to real speed divided by 10. I will remember that here we have go to start again at the beginning of the wave. There. And there, start settings which allow to define the position and the starting conditions of the surfer on the wave. In start setting, you double-click on the wave to position the surfer at the start of the wave. And we can also position the surfer on the board by clicking in the diagrams on the right. We can also determine the orientation and the starting speed. Here are the starting settings. I apply them, and they are registered with the wave. And every time I go with a board on this wave, these starting conditions will be applied. When I click on Go to Start, I go back to these starting conditions. To put the wave in motion, you have to go from stop to start. When the wave is moving, you can change the roll angle, and therefore the trajectory. We can speed up the passage of time to try to maneuver in this wave with our foil. We are falling, so when we have had a fall, we leave with go to start. What interests us is to know what is the reason for the failure. We left with a fairly high speed. We will see that in reality, we will set off at speeds that are much lower. And we are not in a situation of foiling at the start. I'm going to leave with too low a speed to fly. So at this stage, we see that if in the diagram on the right, we are surfing, we have the usual surfing positions. You can change the surfing position. Our departure will be more or less laborious. Are we going to be able to create enough speed to get our foil off the ground? So what we're going to see here is the dashboard, which shows the different forces. These different forces are represented here. We are going to have the global projections, and it is the horizontal projections that interest us. I stop my wave, and I zoom in. The total of our horizontal projection is here. It's about 110 newtons. The total is here, horizontal thrust force. This thrust is made up of different forces. When we are surfing, we have a hydrostatic force, i.e. buoyancy, which by virtue of the slope, has a horizontal hydrostatic component, which generates a horizontal thrust. It is noted here, it is the horizontal component of buoyancy. We have another element here, it's added, which represents added pushes. Here we have an added thrust, because we clicked here on paddling. So I start moving again here, and if I activate front double pulse in the plank controls, in fact, we simulate a push of the arms on each side of 40 newtons for a fixed duration. Its assistance, let's say. We actually include the rowing effect. And this rowing effect, it is seen here in added thrust. We have just passed the foil, we have just passed the flight limit. Here the thrust of the fins integrates the thrust component of the foil, which has a horizontal component. We will see here in the fins the resulting horizontal component of thrust, which is quite small. We see here the horizontal component of the fins. I display the fins in wireframe. We are going to deactivate the following of the board. To position ourselves manually, I am getting closer. What interests me here is that we have a component here, which is a component of horizontal force, which creates propulsion, depending on the attitude of the foil. And this horizontal component of the parts of the foil, we see it here in its entirety. So here we see the sum of all these components, here which propels about 99 newtons, or about 10 kilos. So we have a thrust of about 10 kilos produced by the foil, and the slope. So we could also analyze the different vertical projections. We see that the vertical projections of the fins, so here our foil, is equal to the weight of the surfer. So we can restart the machine. We can direct our force here to the right, following another trajectory. Here we have the horizontal thrust, and below the acceleration. Here, a vision of the angles of attack and roll. The wave caught up with us and we fell. So we're going to go to start. We're going to have to modify something to be able to take off. So we will be able to modify the wingspan of the foil, the height of the wave, the departure speed, all the parameters we want, the surfer's paddling force at the start. We then enter the phase of optimization of the foil. We end this tutorial here. We will see the optimization of the foil in another tutorial.